we are going to go back to the question of how to find the limit of a function. If you remember, this is how we started this chapter. How do we find limits? That was section 2.2. In section 2.2, we could only do two things. And that was pretty much sketching the graph of the function. So this is section 2.2. We would go and create a sketch. In other words, a graph of the function, or we would do a table. Sometimes we would have a combination of both to really verify that our claim about a limit was accurate. So that was okay at the time. It was okay while we were trying to get an intuitive sense of limits, but it was not practical at all. Then came section 2.3. And 2.3 said, okay, we need tools. We'll need algebraic tools that would help us find limits a little bit more efficiently, something that doesn't rely on a graph, on tables. And if you remember, some of those tools were collected at the very end here in this particular diagram. I had a toolbox so that you would think of, okay, we're collecting tools to be able to help us evaluate limits. Some of those tools were these properties that we developed, property 1, 2, and so forth. If you have forgotten them, please go back and re-listen to that discussion. We also talked about the limit of constant functions being equal to the value of the constant. We also talked about limits of the function f of x equals x being equal to a. We talked about limits of power functions where the exponent n is a natural number, and when the exponent is a rational number like p over q. So these were definitely more tools that we had, but if you remember, there was still quite a bit of algebra involved in the computations. So we still we still felt that maybe something else was going to be possible. I don't know if you were feeling like this, but I am sure that a lot of you were probably feeling, okay, this is nice, but it's still a lot of writing. I have to be writing the limit notation who knows how many times. Okay, so now comes section 2.4. And section 2.4 is all about continuity. And the thing is that continuity will make the process of finding limits even easier, more efficient, less writing, less going on. If you remember the definition of continuity, probably by now you're bored of that definition. In other words, if we have a function f of x and we have a value of x, let's call it a, we say that the function f is continuous if the limit as x approaches a of f of x is equal to f of a. And here is the key for evaluating limits efficiently. If you know that the function is continuous at a, if continuity of the function at a exists, then the value of the limit at a is just equal to f of a. That means that by just having f of a, all that we have to do is to evaluate the function at x equals a. We just have to go ahead and do a direct substitution. Take the value of a and substitute it into the variable x in the function, in the expression of the function. So this is why I put here in the title, evaluating limits by direct substitution. If the function is continuous at a, we practically don't need any of these properties, even though they're there, right? And sometimes we are going to use, for example, P1 to P5 if we're dealing with additions of functions, multiplications, and divisions. But the point is that as long as those functions are continuous, I can evaluate the limit of the function just by substituting the value of a into every x that appears in the expression of the function. In the next examples, you're going to see exactly how we're going to put that into practice, but hopefully you're going to feel a lot better about the entire process of evaluating limits. And also the good news is that a lot of the functions that we're going to work with here in calculus are going to end up being continuous. Not always, right? Life will not always be that beautiful, but for the most part, we're going to work with very nice, well-behaved, continuous functions. Let's look at example 1. Evaluate the following limits. That means a here and b here. This is the limit as x goes to pi of this function right here. So what I want to do before I try to make things complicated is to see if the function is continuous at pi. And we already have many properties that talk about continuity. So this is a fraction. I have a numerator and a denominator. And I want to make sure that the numerator is continuous at pi and that the denominator is also continuous at pi, but not equal to 0 at pi. So sine x, sine is a beautiful sinusoid, is continuous everywhere. So that's not a problem. So I'm going to write over here that sine x is always continuous for all x in R, always continuous. And then 2 plus cosine of x, also always continuous for all x in R. We just have to make sure that 2 plus cosine of pi is not equal to 0. So let's quickly test that out. 2 plus the cosine of pi, that's going to be 2 plus negative 1. That's going to give us 1, and 1 beautifully is not equal to 0. So then, by the properties of continuity, I think it was property 3 or 4, we just went over that in one of the last videos. We know then if the numerator is continuous, the denominator is continuous, and the denominator is non-zero, then the entire quotient is continuous at pi. So because we have continuity, we know that in order to evaluate the limit, we just have to take pi and substitute it in x. Here is an x, substitute x with pi. Here is another x, substitute that x with pi as well. So let's do that. So we're going to have that this is equal to the sine of pi divided by 2 plus the cosine of pi. I also want you to note something. Notice how I no longer wrote LIM, the limit notation. It is the practice of calculus, not my practice. It is calculus. So therefore, we are going to follow it by the letter. That once you do the substitution, you no longer write the limit notation. If you haven't substituted yet, and you need to write that expression again because you haven't substituted, maybe you are simplifying the expression, then yes, you have to keep writing LIM. But as soon as you substitute, that's when you drop the limit notation. So now continuing, we're going to have that the sine of pi is equal to 0 divided by 2 plus negative 1. That's going to be 0 divided by 1. This is going to give us to 0. And very easily like this, we have found the limit. Isn't that beautiful? We didn't have to use any complex process or writing LIM 1,000 times. We just came, we argued for continuity. As soon as we determined that the function was continuous at pi, that was it. We knew that we could actually go ahead and substitute pi into the function. So continuity, wonderful, wonderful concept. B, we have the limit as x approaches -2 of this rational function. This is a rational function by definition because it is made up of a polynomial divided by another polynomial. If you remember from the previous videos, polynomials are continuous everywhere. So I know that the numerator is continuous for every x in R, and I know that the denominator is continuous as well for every x in R. All that I have to do is to make sure that the denominator is not equal to 0. So when is the denominator equal to 0? We already solved, we worked with this function previously, so I'm not going to do every single step. We found that this is equal to 0 when x is equal to 5/3. Well, 5/3 is not equal to -2. So then this is telling us that this rational function is continuous at -2. And because it is continuous, I can go ahead and do a direct substitution. -2 to the third plus 2, -2 squared minus 1. This will be divided by 5 minus 3 times -2. Notice how, because I am already substituting, I no longer write the limit notation. All right, continuing, we are going to have here -8 plus 8 minus 1 divided by 5 plus 6. The -8 will cancel out, and we are going to have -1 divided by 11 as the value of the limit. And this is how simple it will become to find the value of a limit whenever the function is continuous. All of a sudden, continuity came and made something that was tedious in sections 2.2 and 2.3 into very easy computations. Computations that were complicated became quite manageable. So from now on, the first thing that you want to do when you're given a limit is to check for continuity at the value of x that you have been given. In this case, at pi, in this case, at -2. If the function is continuous, you can proceed by direct substitution. If the function is not continuous, I shouldn't say that. If you cannot argue for continuity for whatever reason, then we're going to have to find another way to try to investigate the nature of the limit. That doesn't mean that the function has no limit. It may still have a limit even if you don't have full continuity. Remember a removable discontinuity situation, right? For example, I can have a function, imagine a function with a removable discontinuity, a hole right there, at x equals a. And while this function is not continuous at a, it still has a beautiful limit. So just because I cannot argue for continuity, or just because continuity fails, it doesn't mean that there is no limit. There may still be a limit. All that I have to do is to try to investigate the limit in a different way. And we're going to learn more mechanisms for dealing with problematic functions like this. Because like I said, even though most of the functions that we're going to deal with are going to be continuous, there will be a lot of other functions that are going to misbehave. Yet, we're going to have to deal with them. We can't run away from them. I want us to go ahead and tackle example 2 together. As I said over here in the title, this is an AP type problem. Notice what it says, that is connecting several concepts. You know, the AP exam is notorious for that. They just love to create problems that connects many concepts together. The free response problems are like this. You may have a problem with 5 parts, and every single part is really interesting, will require you to use concepts learned in chapter 2, and then part B may require you to use concepts learned in chapter 6, and then part C may take you back to chapter 4. It's amazing how they manage to create one single question where you're going to have to apply many concepts. So here, because our knowledge of calculus is still very limited, I am just choosing a problem that connects some of the concepts that we learned in section 2.2, 2.3, and now in 2.4. So this is not a full-blown open problem. A problem like this may appear as a sub-part of a problem in the AP exam. Anyways, it's definitely a good practice. So example 2 is asking us to show that the function f of x, which is equal to 1 minus the square root of 1 minus x squared, is continuous in the closed interval -1, 1. If you remember, you're going to have to go back now and remember some of the early definitions of continuity in a closed interval. I believe that was video 1 of this section. To have continuity in a closed interval, we're going to have to show that f of x is continuous in the open interval -1, 1. That's going to be task number 1. And then B, we're going to have to show that f of x is right continuous. We're going to show that the limit as x approaches -1 from the right of f of x is equal to f of -1. And C, we are going to have to show that f is left continuous at 1. So the limit as x approaches 1 from the left of f of x is equal to f of 1. If we manage to show these 3 cases, then we conclude that the function f is continuous in the closed interval -1, 1. All right, so let's tackle the first part. Let us begin by choosing a value of x, let's say a, in the closed interval -1, 1. So let's pick a value a that is going to be in the interval -1, 1. What are we going to have to show? We're going to have to show that the limit as x approaches a of f of x is going to be equal to f of a. And because we are choosing a random a can be any number in this interval, any number. So again, imagine the number line right here playing the role of the x-axis. Here is -1, here is 1. We are saying that a is any x value between -1, 1. So we're leaving it completely random so that our argumentation is a general argumentation. So that's what we have to show for continuity. Let's go ahead and try to do that. So I'm going to start with the left. Again, the limit as x approaches a of f of x. Why don't we go ahead and substitute the expression for the function? This is going to be 1 minus the square root of 1 minus x squared. Let me put brackets to keep everything nicely self-contained. And then I know that by properties of limits, I can apply the limit to the first term and I can apply the limit to the second term. So this will be equal to the limit as x approaches a of 1 minus the limit as x approaches a of the square root of 1 minus x squared. And the first limit is just piece of cake. This is just equal to 1. So practically then, we're going to have to analyze the limit of the square root of 1 minus x squared. This is the limit that we are going to have to think about a little bit further. I want you to notice that this function right here is a composite function. The inner function is a quadratic, 1 minus x squared. And then the outer function is a radical function. So in order to evaluate this limit right here, I just want to make sure, what I want to do is to make sure that the radical function, which is the composite function with the quadratic inside, that this function is continuous at a. I would like to figure that out. 1 was super easy, right? The limit as x goes to a of 1 is just 1. It is this limit right here that I'm going to have to analyze a little bit more carefully. And because it is a composite function and the inner function is quadratic, I know that the inner function is continuous everywhere. But the radical function is not continuous everywhere. The radical function is going to be undefined whenever the inside is negative. So I have to analyze the inside function. I have to see what is 1 minus x squared going to dump inside of the radical. We want to make sure that 1 minus x squared doesn't put something negative inside of the radical. So let's see what happens in the interval negative 1, 1. I am going to ask you to try to remember how to sketch a simple quadratic like this one. 1 minus x squared. This is a quadratic with x-intercept of negative 1, 1. And it opens downward. The vertex is at 0, 1. So it goes like this. I only care, however, about what happens between negative 1 and 1 right here. This is my only point of interest. What happens between negative 1 and 1? And look at this. This is beautiful because between negative 1 and 1, the y values are all positive. So pretty much everything that's going to go in the radical right here is going to be positive. So the radical is going to be defined at every x between negative 1 and 1. And if you remember, this is where a is located. A is here. A is between negative 1 and 1. So we're not going to have any issues. In other words, if I pick an a to be this value right here, the parabola is going to give me this as a y value, but that's a positive y value. So the square root of that number is going to be defined. So then that is telling me that this function over here is continuous. This is continuous in the interval negative 1, 1. So if it is continuous, I can continue evaluating the limit by direct substitution. So I know that this will be equal to 1 minus the square root of 1 minus a squared. And this is exactly f of a. If you were to go back to the original function, let's go over here, right here. Look at this. And I were to ask you, evaluate f of a. What is f of a? You will say, not a problem. F of a is 1 minus the square root of 1 minus a squared, which is exactly what we got right here. So based on this, we conclude that f of x is continuous, completely continuous in the open interval negative 1, 1. Now we're going to tackle the last two parts. Let's do b first. Here we have to show that f of x is right continuous at negative 1. Now I already got started with some of the calculations that are identical to part A. I have to show that the limit as x approaches negative 1 from the right is equal to f of x. I substituted f of x and I applied the limit to 1 and to the radical. So practically what I need to do right now is to focus my attention on this limit right here, the limit of the square root of 1 minus x squared. I want to make sure that this function right here is right continuous at negative 1. So in order to do that, In order to evaluate the limit as x goes to -1 of this radical, I am going to check for right continuity by substituting -1 into x. And this is something that you can do in your minds. You don't have to write this down until you're ready to continue with the algebra. If I do 1 minus -1 squared, I'm going to get 0, and the square root of 0 is 0. Great. So then that means that I can proceed by direct substitution. This radical alone is right continuous. So then that's going to be equal to 1 minus the square root of 1 minus -1 squared, which is going to be equal to 1 minus the square root of 1 minus 1, 0. That is going to be equal to 1. And I know immediately that 1 is equal to f of -1. And this is giving us now the desired result. This is showing that the limit as x approaches -1 from the right of f of x is equal to f of -1, f of -1. So then this is showing that f of x is right continuous at -1. Finally, part C. We now have to show that f is left continuous at 1. Again, I already started with the same calculations as in part A and part B. Now the limit as x approaches 1 from the left, the function, the limit is applied to 1, is applied to the radical. And what I have to do now is to argue that the radical function is is left continuous. In order to do that, I quickly do a mental check by substituting 1 into the variable. I want to make sure that when I do that substitution, the radical is perfectly defined. And that's exactly what I get. I get the square root of 0 again. The square root of 0 is equal to 0, so there's nothing problematic about that. So we're going to have 1 minus the square root of 1 minus 1 squared, 1 minus the square root of 0. This is just going to be 1. And 1 is equal to f of 1. So then we conclude here that the limit as x approaches 1 from the left of f of x is beautifully equal to f of 1. So this is saying that f is left continuous at 1. We are practically done with the solution to this problem. This is exactly how you tackle it. What I want to do now, just briefly, is to mention that there is nothing surprising about realizing that f of x is continuous in the interval -1, 1. Here is f of x again. F of x is made up of, let's say, two functions. One, a constant function, and a radical function with a quadratic inside. So if you think about it like this, try to think about this as being the difference of one function, let's say g of x, and this one over here, h of x. So what we found is that this entire function is fully continuous. And think about it. One is a constant function. Constant functions are continuous everywhere in their domain. The domain of a constant function is infinite, all real numbers. So 1 is a beautiful, well-behaved function. The inner function, the quadratic, is also beautifully continuous everywhere. The radical function is continuous in its domain. The only thing with the radical function is that it has a restricted domain. The domain of a radical function consists only of numbers from 0, including 0, to positive infinity. So then all that we had to do was really to make sure that 1 minus x squared would only put positive values within the radical. But because the domain that we were, or the interval that we were working with was the interval from -1, 1, just by quickly sketching the parabola, we notice that the y values of the parabola in this interval ended up being positive, always positive. So then the square root was completely happy with these x values right here. So then that meant that the radical function, together with the quadratic, was continuous in that interval. And we already have a property that says if we are subtracting two continuous functions, then the difference is continuous as well. So this is pretty much the intuitive explanation of the algebra that we went through. This is usually what you can do really quickly as you're scanning through a problem. Think about it. Oh, constant, continuous. The radical function, yeah, but there may be some restrictions. So quickly look at the inner function. What happens in the interval -1, 1? Oh, the inner function is always positive. Great. So the radical will be continuous there too. So really quick way of determining the continuity. It's definitely good to practice that skill so that you can solve this type of problems very quickly whenever they appear in multiple choice problems, because in that way you won't have to write much. You will be able to pretty much conclude all of this just by thinking about the problem in your heads.